Okay, hello everyone. This is Wang Heng from Beihang University. It's my pleasure to introduce our speaker today, Professor Alessandro Parente. Professor Parente obtained his master's degree in chemical engineering at the University of Pisa in 2005. He then carried out a PhD at the same university in collaboration with the University of Utah, where he served as a research associate from November 2007 to December 2009. In April 2009, Professor Parente started working at the Uncommon Institute of Fluid Dynamics. In October 2010, he was appointed assistant professor at the Aerothermal Mechanical Department of University Libre of Brussels. Since 2019, he has been professor at the same institute. In January 2015, Professor Parente founded the Bern Joint Research Group on Combustion and Robust Optimization, involving 7 full-time professors and around 40 researchers. He is currently the co-director of BRIGHT, the Brussels Institute for the Thermal Fluid System and Clean Energy. Professor Parente's research interests have been in turbulent chemistry interaction, in turbulent combustion, reduced order model, non-conventional fuels, and pollutant formation in combustion systems. Also, novel combustion technologies, numerical simulation of atmospheric boundary layer flow, and validation and uncertainty quantification. He is also and co-author of more than 100 papers in international archive journals. Okay, Professor Parente, the floor is yours. You can start.
Thank you. Thank you very much for your introduction. So first of all, I would like to mention that if you have questions during the presentation, I will read them through the chat. So let's try to make it a little bit interactive. I'll try to move this somewhere that doesn't bother. Let's see, yeah, like this. Okay, and so my talk today, and again, thanks to the organizers for this opportunity of sharing our work, is about the use of reactor-based models in OpenFOAM, and I will specifically talk about mild combustion as an application. I suppose that you're all from combustion field, so I don't have to motivate too much. That I would still like to point out what my view is on the role of combustion and new combustion technologies in the future energy mix. I think that we all know this all trajectories looking at our energy supply in 2050 and beyond. They have this idea that we will have a lot of renewable energy, and when we have excess of this energy, then we can store that, but batteries are limited in capacity and time. So it's interesting to also have carriers, and we know carriers like fuels are very good carriers, and store this energy under the form of molecules that could be hydrogen, methane, ammonia, methanol, and many others. But I think that this variety of the energy mix really points out that combustion technologies, and in particular, sustainable combustion technologies, will play a key role in the future. And in particular, when I mean what I mean with this sustainable combustion technology, I mean combustion technologies that respect the environment. So we are engineers, we can design systems that do not pollute, or the emissions where the emissions are quite suppressed. That are flexible with respect to the choice of the fuel, that actually this is also important for security of supply, and that are efficient and that not, I mean, where the energy is efficiently used and is not lost. So this is what you see here is the trilemma. I mean, you're probably used to see the energy trilemma. This is the declination of the energy trilemma for the particular aspect of combustion technologies. Now, if you look at combustion technologies historically, there has always been a need to actually find a trade-off between combustion efficiency and pollutant emissions. This has been known as the combustion dilemma for engineers for several years, because typically you cannot have a very high efficiency without compromising the emissions. But there are some new technologies, and I want to highlight one of them that has several names. I will use mild combustion in my talk, but I mean, it has been known under other names, distributed, flameless. So if you use that names, to not be offended by, it's just for matter of simplicity that I'm referring to mild combustion. So what is nice of this combustion regime is that it allows to actually decouple, in a way, combustion efficiency and pollutants in a way that you can actually reach very high efficiencies without compromising the pollutants, or with having very low pollutants emission. What you see here is a picture of our furnace here at ULB, and you see here on the right, it's when it functions in the conventional regime, where you see a visible flame, you have very high emissions, but you also see when it works actually in mild combustion, and you actually realize that there is no visible flame, although the system is still on, and the emissions are ultra low. We talk about single digits for NOx, for instance, and complete combustion. Also, which is not depicted in this plot, this combustion technologies allows to work with very high flexibilities. Okay, so a bit of the features of these combustion regimes. In flame, you usually have very stable and complete combustion in a very thin flame sheet. What it means is that the heat release happens in very localized regions, and you have very large peaks, which basically induces very large NOx emissions. In flameless, you have very stable, again, complete combustion, but what happens is that you basically transform this two-dimensional flame into a three-dimensional volume. You have volumetric combustion regime, you have distributed energy dissipation, and you basically, by not releasing the heat in one very thin region, you actually create a volumetric heat release, and so lower temperature peaks, smoother transition, and smoother NOx emissions. Beside NOx, also soot is suppressed. It is used, and it's very promising for a number of technology. It's used, for instance, in heat treatments, steel annealing, glass making. It's used for its large fuel flexibility to deal with low calorific value fuels, hydrogen-rich fuels, oxy-fuel technologies, because of the low pollutant emissions and high efficiency. And for the virtue here of being very noiseless, it's also being considered, and there are several applications of that, especially from DLR on gas turbines. So here I showed, the three virtues of this regime and the applications, if you want. Now, if you go on the modeling side, modeling mild combustion and similar technology, flameless, other thing, is quite challenging, because what happens in this regime is that basically, since you are acting in a way on the way combustion occurs volumetrically versus in thin layers, you're basically acting on diluting the charge of the fuel by recirculating with the exhaust gases. And by doing that, you're actually acting on the chemical temp scales. And you see here, this is the typical Rodney-Fox plot, which I adapted to show that basically you are moving a bit up your characteristic chemical scales in a way that they fully or partially overlap more than in conventional systems with the fluid dynamic ones. And so if you look at the Dunn-Kohler number, you approach the Dunn-Kohler number close to 1, which means that while in these regimes of conventional combustion, you might have some scale separation and, for instance, be successful in using flamelet models, here you have to be aware, to be very careful about the simplifications. And in particular, you have to be using models that can account in a good way of finite rate chemistry effects. Excellent. So let's move on. I tried here to, let's say, summarize. There are many plots that try to do that. I've tried to actually do it in a different way as it's usually done, to summarize the existing combustion models in their, let's say, with respect to the size of the typical problem that we have, which is here on the y-axis, and the number of transporter scalars on the x-axis. And so you basically here have the number of computational cells, and you see how the different models, I think, locate on this plot. You have, of course, here on the corner, lump models. Then if you are really interested in very large systems, Fremelt-like approaches are excellent. They provide a very detailed description of mixing, although there are some assumptions on the structure and the manifold on which combustion takes place. On the opposite side, you have, for very small, let's say, systems, you have this canonical reactor, so PFR, PSRs, where you can include all the chemistry you want. Then also, I would like to mention here the PDF-like approaches, where basically I'm talking here about the transported PDF. You basically have no closure. I mean, you treat exactly the chemical source term, but you are limited somehow in terms of size of the problem. And then in the middle, you have these models that would focus on the reactor-based models that can, in particular, include a large amount of finite rate chemistry effects through detailed or semi-detailed mechanisms, and that also can be applied to large systems. I wouldn't talk about CMC, although it's also conditional enclosure models. I think they're also worth mentioning as intermediate choices between the two. So here, just summarize what I was saying. So Fremelt-like approach described very well mixing. It can be challenging with these models to capture finite rate effects, or in a way, it can be challenging to define more dimensions to capture these effects. In PDF-like approach, the chemical source term needs no closure. However, the turbulent mixing needs a closure, and this is where, let's say, there is more uncertainty associated to these models. Now, what we are interested in here in this talk is in these reactor-based models, which provide, I think, an affordable treatment of detailed chemistry. We will see how this is done. And they allow, but of course, they also suffer from some drawback and uncertainties, which is mostly associated to the sub-models that describe the amount of the cell you will see that is reacting and the characteristic scale associated to this process. Okay, looking at the chart, I see there is no questions to be. If you have questions, please feel free to actually ask them. I would like to introduce now this reactor-based turbulent chemistry interaction models, and you basically this goes back to the pioneering work of Magnussen and Chomiak, where they actually assume that there is a part of the cell. Imagine this is your reacting cell. Part of this cell is a reacting fraction, and so the idea is that this reacting fraction that has I mean, it's actually depicted here in a real photograph, can be used or can be described using an ideal reactor formulation. And then the overall or mean reaction rate can be described as the exchange between this reaction and the surrounding flow. So that you see this reaction rate is expressed as proportional to the difference between the properties inside the reacting fraction indicated by the star, the mean properties in the cell indicated by the white tilde, and what you also realize in this formula that there is a gamma. Gamma is the mass fraction of this reacting fraction in the cell. So how much of the cell is occupied by the reacting fraction. And then you have this tau star, which is basically the time, the residence time of the Feng structure in the cell. Now, we need the model to get these properties because we are not solving. The cell doesn't solve the reacting fraction, so we need a model to characterize this subgrid quantity. And to do that, we actually use a reactor model. In this case, we use just a PFR, actually a batch reactor here. We actually do that in a time splitting approach. So we solve a set of ODEs to get this concentration and density in time, and then we plug it in this formula and we get our reaction rate. Now, as I was mentioning before, we have a number of parameters that we have to model here. The first, as I was saying, is the evolution of this mass fraction. This is done by assuming a certain idealized reactor. Then we have to estimate the residence time. Sorry, there is a problem here. So this should be here. So it's a fine structure residence time, tau star, and the fine structure mass fraction, which is gamma. And you see them here in this plot. So people in the audience, is there anyone in the audience that uses the EDC? Maybe you can just indicate that by raising your hand. I will be then aware that there are people that have been using these models. But basically in the EDC model, I highlighted here, you have this gamma, so the mass fraction of the reacting structures of the fine structures, and the tau star, which is the residence time. So you see that these are obtained directly from a cascade model, very similar to the energy cascade model. You see, you have a mean flow, and then you have a final scale where everything is dissipated. But here, this is applied directly to it's applied directly to the chemical process. And so combustion is assumed to be happening at this scale, which is indicated by this star, where all the dissipation of the mechanical energy occurs. And so by actually doing some math on this, the authors of this model were able to provide a direct link between these subgrid quantities, so gamma, lambda, and tau, and the main properties of the flow that you solve on the numerical grid. So you see that the mass fraction of the reacting fraction and the residence time are directly related to quantities you know and you transport, which is the dissipation rate, kinetic energy, or properties like kinematic viscosity, yes, through some constants that you have to determine. And there has been a lot of research on that I won't have the time to focus on. In practice, how this is implemented, for instance, in softwares like OpenFOAM, you basically have the different unknowns here and from which kind of, let's say, input they come from. So you have the mean mass fraction. This is from the internal field of which is provided within OpenFOAM. The star, so which is the fine structure property, comes from the fine structure model, which is either a perfectly steered reactor or a plug flow reactor. And gamma, lambda, and tau star, they both come from the energy cascade. Okay, so now I will not talk much about the EDC. I would rather focus on another model, which we have worked on a lot in the last couple of years. And we're also trying to improve. And this model is the partially steered reactor. Now, in this model, the difference with respect to the EDC is that we specify, although you can find actually analogies between the two, and you find also equivalences between the two, is that now you prescribe a certain model form for your gamma. You say that your gamma is given by this relationship. So it's the ratio between the chemical characteristic time and the sum of the mix and the mixing and chemical times. Okay. Why you do that? Because as we said, the reaction occurs in this fine structure. So the idea is that this gamma would be proportional to the ratio between the time spent in the fine structure for reacting and the total time. What is nice of that is that you get a gamma that depends directly on the Dunn-Kohler number. And this formulation respects, unlike the EDC, a few properties or constraints that are interesting. In particular, for a Dunn-Kohler number, which is very small, so going to 0, which means that you tend to a perfectly steered reactor, you get a gamma equal to 1, which makes sense. It means that all the cell will be reactive. Okay, so this makes sense. For a Dunn-Kohler, which is very, very large, you get also something which is making sense because you will have very strong mixing, and means that gamma eventually asymptotically tends to 0. Now the problem, or let's say the challenge, is how you actually get these characteristic scales, because now we have moved the burden of modeling from the cascade model, if you compare to EDC, to actually having a model for this tau C and tau M. So for the tau C, you have several choices, and these are the ones we actually used in our OpenFOAM implementation. You can actually base this chemical time scale on the reaction rates, or on the species formation rates, as you see here, or you actually do something more involved and costly, which is basically finding the Jacobian matrix eigenvalues and then looking at the controlling scales. For mixing, you also have many choices. The simplest one is to use global models where tau mix is just a fraction of the integral time, or you can do something a little bit more fancy. You introduce a fractal quantity here, like Golovchev proposed in 2002, or you can use very local models, which means that you solve transport equations for the scalar variance and the scalar dissipation rate, and this ratio would give you a mixing time. Okay, now if you look at the passed model and its implementation in OpenFOAM, it's very similar to EDC because YK now comes from the internal field as before. Y star comes from the fine structure model as before. But here for gamma, we don't have a cascade model, we have a direct relationship. And the same, I'm just pointing out one example here, we have a model for the tau star, okay? But as I was saying before, this is just one option. The other options are also present in our implementation. Okay, so how this is this code called? So our suite of code is called Firesmoke. This is from a very strong collaboration with Alberto Guocci and his teammates at Milano, Politecnico in Milano. It's basically a finite rate solver for combustion simulations. It's a collection of pressure-based solvers based on simple pimple algorithms for both runs and LES with detailed kinetics. The combustion models available are EDC and PAS. Actually, there are also the simpler version of EDC, which is ED and the EDFR, eddy dissipation and finite rate chemistry. And we actually handle the chemistry through OpenSmoke, which is a software. Probably many of you know this software. It's a software from Politecnico di Milano, which handles very well, very detailed chemistry. I don't know if there is anyone from Milano connected here, but I mean, this is really very useful for handling chemistry with respect to the native, let's say, capabilities of OpenFOAM. If you are interested, this is the QR code. I'll leave you a second to actually scan it and land on the page where we actually host this implementation. There is also a number of publications you might really be interested to read before using this code. Okay, let's go on. This is what I was mentioning before. This is how the chemical mechanisms are handled inside the code. You see that at this point, after in the simple pimple algorithm in the transport step, this is at this time that the chemistry integration happens, and this actually goes through the chemistry step that is handled in OpenSmoke. And this ODE integration that I was mentioning before. So the let me go back so that you see what I'm referring to. This dy over dt. So this ODE integration, if we use a batch model or a PFR model, is handled within OpenSmoke, and two different, models are possible. PFR or batch reactor, which is, I mean, almost identical, and PSR, which is actually the original, let's say, reactor model that was proposed by Magnussen in EDC. So these are the combustion models available: eddy dissipation, finite rate, eddy dissipation concept, and PAS. In OpenSmoke, we perform all the fine structure property calculations and the ODE integration. Then this is going back to the solver where the chemistry integration is included. Okay, let me maybe move on. I won't say many other things about the code itself. I think it's more interesting that I present a little bit the results that we obtained with this code for a number of cases, going from very easy, let's say not easy, but lab scale systems, well characterized, that is what I meant, to more industrial-like systems where we have less information to validate our model. So the first one would be the Adelaide jetting outco flow. Many of you know that probably. This is a prototype flame, has been used for mild combustion. It doesn't have the typical recirculation that you have in mild combustion systems, where the dilution of the charge is driven by, let's say, this mixing with the recirculation. Here, the recirculation is achieved by artificially, let's say, diluting the co-flow by using an upstream burner, okay? So that you have in the co-flow combustion products and some oxygen. Particularly, you have 3 levels of oxygen, 369%, to show, to see what happens as you increase. And of course, the most challenging case is 3% because this is the most diluted one, less reactive. You have 3 Reynolds number, co-flow temperature 1300. Diesel allows to have, let's say, reaction going on. You have the fuel, the hot co-flow, and also to mimic the fact that you have a mixing with exhaust, of course. And you have 3 streams. So you have the fuel, the co-flow, and the air. Here you see some run simulations to start with on an axisymmetric grid using a K-epsilon model with round jet correction by Pope. Also other models were used. We actually used 2 kinetic models here. The Key 58, which is a 17 species AD reaction mechanism, and the GRI that you all probably know. And then we actually used the discrete ordinate weighted sum of regases model for the radiation, although I would like to point out that the radiation here doesn't really play a major role. Also, we have data at different axial location along the axis. So we have 30, 60, 120 millimeters. We also have the axial information to compare with. Okay, so what I wanted to show here was the impact of the mixing models that I was talking about before. So let's have a look at the different lines so that you understand what every of them represent. I'll also have a look at my clock. Okay. So you have first a global model with a C mix of 0.6. So it means here I have 0.6 times K over epsilon. This is a fractal model, which means that you have the integral time times a term that depends on the C mu and the Reynolds and this fractal constant. And then you have 3 local models, which means that we solve transport equation for the variance and the scalar dissipation rate. And you know that in the scalar dissipation rate equation, there are sets of coefficients. There is no, let's say, consensus on them. And so we use 3 of them. And so basically what you see is that there is a huge impact of these mixing models on the results. But what is interesting to point out is that if we go, if we stay with local models, we don't see, of course, we see less differences on temperature profiles, but when we go to CO and OH, we see that the role of the mixing models, in particular, the using a mixing model local, has an impact, and this impact is reflected in the predictions of CO and OH, which become much more reliable, let's say. Okay, now let's have a look at what happens at if we try, let's say, to find what would be the ideal mixing constant in this case. What is interesting is that when you look at the different local models, they provide you, you see, with a distribution of the equivalent C mix that you should have if you were using a model like C mix times K over epsilon, okay, over epsilon. So you see that basically a non-constant distribution of C mix is, in this case, the key to get good predictions. And this is accomplished only by using these local models. When you look at the fractal model, you see that there is a very small impact of this fractal term, and mostly the C mix equivalent stays around the value that we have specified in the global models, which was 0.5 in this case, okay? What is also interesting, if we look now at a dynamic model, so a local model, in this case, the local model with the coefficients of Chen, what we see is that this C mix, it basically increases moving downstream, and then you see a decrease, okay? In particular, also what you see is that if you compare 3060 and 120, you realize that you have higher C mix as you go further upstream in the flame. But I mean, the key observation here is that a non-uniform distribution of C mix is obtained, of course, with these local models, and this is really important to achieve good results, good predictions, not for the main species, as I was mentioning before, but for the minor ones. We then applied LES simulation. This was a paper published by my former PhD student, Ji Lee, now in Cambridge. And she's not more in academia, but she still is in Cambridge. And we actually intended to do this work to understand what was the importance of the closure in mild combustion. And so we took the same case, the Adelaide jet inert flow, and we actually you see here the different settings, different meshes, the inflow generator. If you're interested, we use Limus. And then, of course, we use the passive pimple smoke in this case. One equation for viscosity model. And we use PAS, and then we compare that with no closure. Means we consider submodels of PAS where gamma, so the fraction of a reacting cell, was actually set to 1. And when we compared different mechanisms, a multi-step global mechanism and a skeletal mechanism, so that you have here. And what you see here again is that, again, we see no major differences on temperature predictions, which actually kind of intuitively tell us that basically the importance of closure in a system that is very close to a very small Dunkel number is small, as we should have expected. And also, if you look at the fluctuations, we have more or less the same kind of observation. When we look at the major species, more or less the same. You see here CO, and you also see the fluctuations of CO2. But then when we look at the minor species, we also conclude very similarly that the three formulations here, so this is the PAS, so this is the quasi-laminar finite rate, means that you basically take the PAS model and you put gamma equal to 1. And the laminar finite rate simply means that we solve equations without closure. And you see that the differences between them are not very substantial, or let's say always within the same range of uncertainty or within the experimental uncertainty range. And when we look at the reason for that, as we were expecting, this is related to the fact that the Dunkel number in this flame is very, very small. So you see here the distribution. I think we reach values that are well below 1 all the time, which means that basically what you see below, that is the mass fraction of the reacting fractions in the cell, are very close to 1. Here, do not be fooled by the fact that the scale starts at 0.8. So it means that even here, when you see blue, that's a very large number. And this large number is all the time or very often above 0.9. Okay, so we have this, I mean, at the same symposium, I think there was a paper showing that in LES you could actually sometimes, let's say, use these models without closure in specific cases, of course. So this doesn't apply to all cases, in particular to cases like this, where you have very low Duncker numbers and very small fluctuations, like in mild combustion. This could be the case. Of course, TCI, so I'm not saying you don't need TCI, you need them for sure, and I will show you that you need them to capture out-ignition and local extinction phenomena. We then moved on, and we also applied this model to modeling other flames which are characterized by shaded flow flows. And what such flame is the Cabra flame. That is, you have actually two fuels. So we focused on CH4. The Reynolds number jet, the Reynolds number of the fuel jet is higher here. Co-flow oxygen is not very low. I mean, it's about 15%. So it's not exactly mild. It's a fish shaded co-flow. The co-flow temperature is similar to the Adelaide jet inert co-flow. It's 1350 Kelvin. And you have two streams. You have a fuel and a not co-flow. And the important thing here was that we wanted to have a challenging case to test the impact of these local mixing models, in particular, the impact of uncertainties in the turbulent dissipation rate transport equation, in the, dissipation rate transport equation for the scalar that we actually use for the evaluation of the mixing time. And so our intention was to say, okay, now we have a mixing model that depends on two transport equations. So we have the variance, scalar variance transport equation and the scalar dissipation rate transport equation. And here you see the equations, but in these equations are, you have parameters that are, as I was saying before, uncertain, that in our code, of course, can be set in this combustions option dictionary. But we wanted to use this case to actually see whether we could find optimal values for these constants. And in particular, we wanted to see whether these optimal values that we obtained were in line with our observation, empirical observation of the different models that we had carried out before on the other systems. So what you see here is the impact. So this is the results of our model. So fire smoke on Cabra flame. And you see basically the impact of using a global model here with two constants here, 0.1, 0.5, and a local C mix, which actually solves, comes directly from the solution of these two transport equations. And so what you see is that, of course, with a local model, you get a much better prediction of the temperature rise. With the C mix of 0.5, you get closer to that, but you are not able to really follow the profile. In particular, not in space. This actually confirms that you would need a local distribution or like a non-unique value of C mix. And then based on that, what we did was to perform a forward UQ propagation coupled with polynomial Gauss expansion. And you see the results here. Basically, you see the results of our predictions compared to the experimental values. What you also see is the range of the predictions which are obtained with the different sets of values associated to the scalar dissipation rate transport equation that we found in the literature. What we basically did was to run a large number of simulations in a range of values for these coefficients here, CD1, CD2, CP1, and CP2. And from that, we built a response surface. We used polynomial Gauss expansion to get this posteriori distribution and to basically find a least square point that would provide the best results compared to experience. And what is nice is that we were able to confirm observations that have been made in the past by other authors regarding the relative importance of the different coefficients of the model. So we were pointing out the two most relevant coefficients and the range of values, the optimal range of values for them. So if you're interested, this is impress in the latest proceedings of the Combustion Institute. Okay, so now I also wanted to point out, I think I'm moving towards the end of the presentation. I wanted to point out the use of this model for more realistic systems. We have a furnace at ULB. I showed you in the beginning the pictures of the flame in the system. Again, this is where the system operates in mild combustion. This is where in flameless regime, this is when it works in conventional flame regime. You see a picture here of the furnace. It's fired with a vertical burner, reverse flow configuration, meaning that the exhaust gases exit from the same side. You see it here. So the air and fuel come here. There is the combustion. It's a reverse flow configuration, meaning that the exhaust gases then pass through the heat exchanger that you see here on the side. The heat exchanger aims at heating up the air so that you increase the efficiency of the system. So we have a cooling system to actually control how much heat we lose because the system is well insulated. And then we have ports to measure temperature. We also have optical access to do chemiluminescence and other techniques. What is nice here is that we did an investigation adding hydrogen. So going from basically 100% methane to 100% hydrogen. And as you can see in the different plots, these are plots taken at different locations here at different ports that are indicated here. You see very drastic change in the behavior of the system. The system is fully mild and flameless when you are working with methane, so the black line. And then if you look at what happens with 100% hydrogen, you see very sharp rise of temperature. This happens as soon as you reach 50% of hydrogen in the mixture, okay? This is by volume, okay? So this is what happens here. You see that you have very, very strong impact. So we wanted to capture this with our model. Before that, I wanted to show you that also the appearance of the flame is very different. So here you have what we see with the chemiluminescence looking through the optical access that we have on the furnace. You see that basically with the full chart of methane, you have no combustion. I mean, no clear reaction region. Everything is distributed. And then as you start to add hydrogen, then what you see is that you basically get something which is almost fully attached and very high intensity. So it means that basically your system is actually deviating from the condition of mild. Now, if here you would be using a model that doesn't allow to follow this, you wouldn't be able to, let's say, see the impact of this change in structure. And so it's important that your model can follow that. And the fact that your, let's say, the pass model has intrinsically a Dunn-Kohler number inside allows it to adapt to every regime, basically. So that's why it's important. And I don't wanted my message before was misleading. I said that in the Adelaide jetting hot flow, the importance of subgrid closure was not important, but you will see here that it is very important because, of course, here I wouldn't need probably to have a subgrid closure because everything is well mixed. It's chemistry controlled. It's basically a big, perfectly steered reactor. My Dunn-Kohler number is very small, 0.02. But then as I start to add hydrogen, I have peaks of temperature that are very pronounced. My system is not mild anymore. If I didn't have a subgrid model, which is embedded through the formulation of gamma and the residence time, then I wouldn't be able to capture now another regime, which is completely different in the same furnace, going with methane to hydrogen. Now what I have is that I have something which is almost fully mixing control, and Dunn-Kohler number, which has a maximum, and you see here, I mean, it's not very clear, but it's here really close to the burner exit. It's a maximum of 22. Okay, so it's a big difference. So with that, I finish this part. I want to maybe spend a few minutes showing where we are going, okay? So I showed you this slide already. Where everyone would like to go is here. Models that can actually do a lot of chemistry and very huge problems. Why? Because we are very far still to be very good in predicting fluid flexibility, fluid information, flame structure, and all these very complex phenomena. So I don't want to spend too much time on that, but basically, the message I want to bring is that the data science can actually help us a lot in that, because we have a lot of data available from theory, experiments, and simulations, and these can all be used in actually making this step that we want to do towards these better models. There is one challenge, though, that most machine learning applications are not physics-based. They have a lot of data, and each new, let's say, prediction a very small impact on the prediction. Okay, I mean, the cost of every evaluation is quite small. But here, in our cases, we know that we have very strong, very intensive, from a computational point of view, simulations. They are physics-based, and the data are sparse in the sense that we have maybe we have a lot of data for specific conditions. Think about DNS, and then we have not enough data at all the Reynolds number, all the Duncker number, all the Karlovitz number that we would need. So I would like to briefly talk only about one point. How can we use data science to improve the combustion models? And I would like to refer to the combustion models I was talking about, so the reactor-based models. If you look at the trends in data-driven science, you see that some people are looking into replacing the mean reaction rate with a model. It could be a fully connected neural network, a convolutional network, or the spin-offs of this convolutional network like GANs. Other things that you can do is that you can actually correct the reaction rate with an OTCI correction, which basically means that you have a term which is not considering turbulent same interactions, and then in front of that you can put a correction term. I think that the Yuki Minamoto from Tokyo Tech is working on that. Or you can actually do the same correction in the framework of models like the reactor-based models, where you actually impose a certain model form, which has some advantages, like the one I was mentioning before, that you have a way to treat chemistry in a good way. Okay, something that we have done is that we have looked at data from DNS from our colleagues in Cambridge, Dr. Chen, Dr. Doan, Professor Chen, Professor Doan, and Professor Swaminathan. And the intention was to actually see what was the impact of, what was the performance, let's say, the a priori performances of this partially serial reactor model using DNS data. And so we saw that, in fact, the definition of gamma in the model is suboptimal. So it means that it doesn't really represent the complexity of the problems that we can find in DNS data, and in particular, this DNS data that was referring to mild conditions. Another thing that we also pointed out is that in the Passer model, the role of the fine structure is crucial, is key. What you see here is basically a comparison between a model, partial serial reactor model using a certain model for the fine structure, so the PFR, and the same model where we just consider the laminar finite rate. And you see that considering a model for the fine structure has a huge impact on the results. I don't want to, spend too much time with this, but you can guess that the model that you use for the chemical time scale evaluation will have a huge impact on the results. So here you see some of the models that we have been testing, the formation rate, this is this one, or for instance, a model that is only based on, let's say, is loosely based to the Jacobian matrix, so the tangential stretch rate. What I wanted to show here is the impact that the formulation of the chemical time has on gamma. So kappa here is the same as gamma, so don't get confused. This is just the mass fraction of the reacting fractions. What you see is that you have a huge variability of results. And this, of course, has an impact on the final predictions. Something also that we looked at is, yeah, maybe I show here. I show what would be an optimal chemical timescale formulation to actually be able to improve the predictions of the variables of interest. So all of that was done, let's say, a priori. And you see, and it's interesting that the optimal timescale is not just one timescale, but it's the mixture of different formulation of the timescale. And this is actually something not difficult to understand. In a way, this is related to the fact that in different regions of the flame, you have different phenomena taking place. And so the different definitions of the chemical timescale would capture these different phenomena locally. We also tried to see whether we could actually use the supervised clustering or semi-supervised, if you want, clustering approach in finding this optimal formulation. And you see here the comparison. We are basically finding out that this is here the optimal error that you would get by minimizing the error in the reconstruction. We were seeing that we would get close or closer to that by conditioning the data twice on the mixture fraction and the scalar dissipation rate. Or also, I see here, yeah, other variables. I would like to finish with this work that is also a work in progress. It's basically an idea that we got by looking at the research of Steve Brunton and this work on sparse regression, sparse representation. The idea that we have is that we can improve the formulation of gamma by using DNS data, and basically by using an approach that would allow us to select what is the most appropriate model form to describe gamma. And so this is the work of one postdoc in my group, Rodolfo Freitas, and you see that basically you get a regression with a penalty term. This is a standard Lasso regression. The objective is that you want to minimize the difference between the predicted mass reaction rate and the DNS ones. But with the penalty, you actually want to favor sparse solutions. And what this approach tells us is basically that there are some forms of gamma that are better in terms of sparsity and predictivity compared to others. Now this work is under preparation and submission, so it's not available at the moment. As we send it in review, we will publish also an archive. So if you are interested, you can reach out and we will share it. Another possibility, and this is the last one, is that we correct also our reaction rate from the partially sterile reactor model with some term that can be coming from neural networks. So you see here, for instance, that we can use neural networks with inputs from DNS data, and this can help us define a correction term so that our model preserves a physics-based, let's say, part and a correction term which is data-based. You see that with this approach, we are able to improve very much the prediction of the heat release rate. You see in this plot the heat release rate from the DNS and the pass-through model, and then you see the heat release rate from this improved PSR model. Okay, with this, I will skip to the conclusion. I think here you have again the QR code to actually go to the page of Firesmoke. I think I tried to convince you that I'll show you the power of this reactor-based model in treating finite rate chemistry at an affordable computational cost. They can be applied to both mixing and chemistry control regimes. They depend strongly, and they underline strongly on submodels for the characteristic scales, and should be coupled, I think, with the data-driven approaches to improve their predictivity and reliability. And with that, I conclude, and I thank the sponsors that have sponsored this research. Thank you very much.
Okay, thanks. Thank you, Professor Parent, for the very nice and insightful talk. Let's move on to the Q&A session. Currently, no questions from audience.
Yeah.
Maybe I can start. On page 42, you mentioned that the model can be used to switch from the chemistry controlled to mixing controlled. So what's the criteria to determine the...
Yeah, this is done automatically by the model, because let me go back here. The model has embedded this this Dunn-Kohler dependency here.
Dunn-Kohler number, okay.
Yeah, which means that as you go to a regime where the Dunn-Kohler number is much higher or smaller, this will adapt the reacting fraction, and so the model will behave differently.
Okay,
if you are in a regime which is very small Dunn-Kohler number, this gamma will become large, and if you go to a regime where Dunn-Kohler number is large, then gamma will progressively become smaller.
Mm-hmm. Okay, so you need to define a critical Dunn-Kohler number, right?
We defined the Dunn-Kohler number just comes from these sub-models that we defined for the chemical and the mixing time scales.
Mm-hmm. Okay, thanks.
So we don't define a critical Dunn-Kohler number, but Dunn-Kohler number computed locally adapts the model. It's the other way around.
Okay, clear.
But your point is good in the sense that we have seen with Rodolfo that, and also with Arthur Pécan, while he was in Cambridge with Salvatore and G Chen. I think G is connected. I saw him. I think that we saw that this gamma sometimes moves too fast towards 0, which means that we might need to either change the model form, which is what we're doing, but also maybe define threshold values for the Dunn-Kohler number.
Mm-hmm. Okay, thanks.
You're welcome.
Any questions?
Can you? Yep.
Hi.
Yeah. Go ahead.
Hi, Alessandro. Good to see you.
Good to see you. How are you?
Good to see you. I'm very well, thank you. And you look very well as well. Long time no see.
Yeah.
It's really been a long time. So it's a really insightful and inspiring talk. I just have a quite general question regarding the things we do. Is it TCI really as the effort? And if yes, when? Clearly, I think you have already shown in your Adelaide case, sometimes it does not really make a big difference. And actually, if you can put on a really fine grid, the uncertainties you reduce by using a brute force, compared to having to optimize your coefficients. And how do we do this balance? And that is really a question. And regarding the filter size or the grid size, do we have an idea how big is the line where we can actually use no model for turbulent combustion simulations?
Yeah, I think so. I try to answer to the question in two parts. First is, do we need disclosure? So I think that the example of hydrogen is a good example, because the same furnace, flameless furnace works. I mean, it was designed to work in flameless conditions. Then you start using hydrogen, it's not flameless anymore. And in particular, hydrogen has this very specific behavior that if I then didn't use a pulse model, I wouldn't be able to actually capture this combustion behavior accurate or properly. So what I'm trying to say is that in the perspective of having flexible charges, I think, and in particular with these fuels that might be altering the structure of the flame speed very strongly. I think that in this respect, it's always important to have a model can be more general. At the same time, I also see your point and the fact that there is more and more evidence that with an appropriate grid in the LES kind of context, the importance of this subgrid becomes less relevant. And I think one criterion would be to look at the local Taylor number that you have, let's say, at the scale of the grid that you are resolving. And this would be a good indication whether your grid is fine enough. But it's not something that you could, I would say this, know a priori, right? So it's a bit complicated. But I agree on the fact that it's a question whether this correction is needed. I would say, for sake of generality, it is important, in particular in the perspective of having fuels with very distinctive, very different behaviors. And although there are uncertainties, and this is where I actually advocate the use of data-driven science to look at conserve this certain physics-based nature of this model, but to plug in knowledge that is too complex for us to manage in a model form, and that we have to manage differently. You know very well, you have worked on this data-driven approach to get the filtered, so the joint PDF. So the amount of the complexity of these models is so large that you can't probably account for that globally. But this is the very reason why I think it's important to do this in a corrective way. So what I mean is that I don't think it's very useful to replace a full model with the data-driven model, but it's interesting to correct a model form with a physics-based with some kind of data-driven correction.
Yeah, but in this case, I suppose the data set itself and how general your data set is becomes another important question.
Yeah. So this is important. This is very important, and I think the less you put all together, the more general your correction will be. So I give an example that I think it doesn't come from my group, but I found it a very clever way to do it. It's from Yuki at Tokyo, Yuki Minamoto. So he has this correction that it actually divides in two corrections. One to describe the regime, and one to describe the amount of reaction fraction amount of cell that is reactive. And by doing that, he shows that these corrections become more universal because they apply across data sets. So this concept of transfer learning. And I think this is what you have to do. Rodolfo in our group is trying to, actually he did already that. He tried to get this correction factor on 2D DNS and apply that to completely different 3D DNS. We have to go in this direction of do transfer learning, generalizing. Otherwise, it becomes it's still very challenging. Yeah.
Yeah. Okay. I have another small question regarding your transport equation for the scalar dissipation rate. I didn't know you were solving that. And why was the reason for not using a algebraic model, which I think is quite.
Which model?
Is with the scalar dissipation rate model.
Algebraic model, you mean?
Algebraic, yes.
Yeah. So actually, I think we tried that, but we basically because behind the algebraic model, correct me if I'm wrong, there is also strong hypothesis on how this dissipation takes place, right? And so we basically land into a condition which is very similar to assuming a global CMix. So the real distribution of mixing times that is suitable for the specific case, we only get it by solving this equation, which is also, I mean, of course, introducing uncertainties. And then I get your point, because then now you have to deal with these uncertainties and this lack of consensus. But if you use an algebraic model, we don't see, I mean, we get a less performing model in general.
Okay, so there must be a leading order effect that comes into place.
Yeah.
Okay, I see. Because by solving such a complex model, you also have to deal with the numerical, uncertainties. Yeah.
Something I wanted to try, but we didn't yet try, is to actually use the model, which I suppose you also used. These models for dissipation rate, which is not the classic model 2D grad F. It's a more sophisticated model. I think we have looked a little bit into that a priori, but we didn't look at that during the simulation. And this is a great suggestion. We will look into that. Yeah.
Okay. All right. Great. All right. Thanks.
Thank you.
Okay, thanks, Tim, for the questions. Huang Wei, do you want to ask questions?
Yes, I have a small question. Hello, Alessandro. So you mentioned in your slides, I think slides 26 or 27. So you also tried no non-closure model, right?
Yes.
So one is so-called LFR, and another one is QLFR. So what is the difference between them? Maybe I missed some key information.
No, it's you are completely right. I didn't explain the difference.
Okay.
So QLFR is simply a partial model where let's say here, it's a partial model where I impose, let's see this one here. It's a partial model where I impose gamma equal to 1.
Oh, okay.
We call quasi-laminar finite rate. And the laminar finite rate is simply the model where we don't have any time splitting, and the reaction rate is calculated using Arrhenius equation directly, no closure at all.
Okay, so when you put gamma equals 1, that means what does it mean?
It means that the entire cell is reactive.
Oh, okay. And then your 1 minus gamma equals 0, right?
Yeah, but I don't have in past. In fact, we don't have the 1 minus gamma anymore. This is a typo here because actually this is wrong. So you would have 1 minus gamma if this was y0, but we don't have it. So please, I will send maybe the corrected slides, because this term is not there. It would be there if I was considering the surrounding fluid.
Okay, I see. Okay, so this is my first
but thank
question.
you for pointing it out. So this is a mistake. This term is not here.
Okay, never mind. Okay, so my second question is for PSI model, is it actually accurate enough, or it is actually possible to use it for predicting some like a blow off, some flame dynamics with very strong unsteadiness, right?
So we have never tried that, but we have a gas turbine, a micro gas turbine chamber here, where we actually are studying ammonia hydrogen mixtures, and we have these problems of blow off with ammonia, as you probably can imagine, and we see that to some extent we are able to predict it. Now we didn't really perform a comprehensive and complete dynamic study to see that. But in principle, I think the model has the ingredients to do that.
Okay. Okay. Thank you. Thank you very much. Yeah.
Welcome.
Hello, Professor Parente.
Hello.
I also have a question regarding the scalar dissipation rate. I mean, is there any specific advantage for solving this the transport equation for this scalar dissipation rate? I mean, if the difference is small, I think maybe we can save the computation time without solving this additional equation.
Can you just repeat the last part?
Okay,
I understood the first part.
Is there any specific advantage by solving this the transport equation for the scalar dissipation rate?
Yeah.
I mean, is the difference large, observable?
Yes. So that's a good point. So you see here, this is Cabra flame. And you see that in the Cabra flame, you have this autoignition process. So what we saw is that if we have a model with the constancy mix, we kind of get that right, but I mean, with some discrepancies, but we get close to that only when we solve this scalar dissipation rate equation. Now, the question that you have is this difference enough to justify the additional cost? Now, additional cost is not huge because it's just a transport equation. The problem for me is more the uncertainty that we have in these coefficients, which is very large uncertainty. Now, what you see here is this is the result that we get with the optimum, but the optimum, we don't know that a priori. We had to perform a study to get to this optimum. You see that the center line is kind of okay with the green curve, which is specifying a C-mix of 0.5. The same happens at Z over T of 15. But then as you move downstream, the discrepancy increases. Now, another approach would be that we somehow get a data-driven model for this mixing time. But I still don't have a clear idea how we can do that in a way that is not very case specific. But I mean, this is something to work on. But I get your point. In some regions, there is not a huge difference. In some other regions, the difference is more important, like here, downstream of the flame, which probably means that your C-mix here had to be larger than 0.5.
Okay, thank you. This is the first time I saw people solving this scalar dissipation and transport equation. So do you have the reference for this equation? Can we find it in your paper?
Yes, it's in the paper. You will find all the details. But I don't know if the paper is, I think it's online. Let me see if I can give you the.
Okay, I will
see if I can share the link in the chat. Yes, it's there. Yeah, so if you see the chat, I am putting that in the chat.
Okay. I have no further questions. Thank you.
You're welcome. Do you see all of you this link?
Yes, we can see. Thank you.
Okay, good.
Okay, thanks. Any questions from audience? Okay, if no further questions from audience, also time is up. Let's thank the speaker again, and also
thank you very much.
Yeah, thank you audience for attending the webinar. Wei, can you summarize the talk?
Okay, so thank you, Alessandro, and everybody, please open your camera and thank the speaker again. Okay, so have a nice weekend.
Thank you. Let me unshare my screen though. And thank you for the invitation. If you have any question and curiosities afterwards, you can reach at my email address, and I will be very pleased to answer your questions.
Yes, no problem. Yeah. Okay.
Thank you.
You take care. Bye-bye.
Nice weekend. Bye-bye.
Bye-bye.
Bye-bye.